Yes. Welcome all of you to the today's section. So today we are going to discuss a new concept called interpolation. So what actually this interpolation in this unit will do? Suppose you assume that f of x is a given function. F of x is a given function. Okay. So we are going to approximate the given function f of x by polynomials say p of x. Okay. So what about these polynomials and how these approximated polynomials will be helpful to us? One thing, suppose if we do not know what is f of x, in the entire domain, but we know the values of f at some points. We know the values of f at some points. That is, suppose if this is our domain, interval a to b, we do not know what is f of x, whether f of x is equal to sin x, or whether explicitly we do not know. Okay, but what we know is at certain points of the domain, we know the function values. So what is f at a, what is f at x1, what is f at x2, what is f at xn minus 1, and what is f at xb. So these values we know. So only a finite number of values of function f we know it. Now suppose if we have some approximate polynomial p of x, since we do not know the function exactly what is f of x, then suppose if I ask at this point y, what is the function value f of y, we do not know, right? Why? Because suppose if we know, suppose f of x is given to be some sin x times e to the power x, what we can do, we can simply use this function to evaluate the value of f at the point y. At the point y, right? But this is not the situation here. This is not the situation. But what we know, there is a polynomial p of x which approximates the function f of x. In this case, instead of finding to find what is the value of f at y, what we can say, the value of f at y is approximately equal to the value of the polynomial at the point y. Not only at this point, at all the remaining points of the domain, what we can say that the value of the function f is approximately equal to value of the polynomial at the y. Okay. Now here, how to choose this polynomial? That is the question. Okay. That construction we will see little later. Let us first understand what we are going to do in this unit. Okay. So this is the first use of this approximating polynomials. And the second one. Second one is suppose if you want where f of x is not known explicitly. So suppose to find roots or derivatives, or to find the integral values for the function f, what we have done previously in the first use of this approximating polynomial is basically to guess what could be the function value at that point y. And the second one, to find the roots of the function f of x is equal to 0, or the solutions of the equation f of x is equal to 0, or to find the derivatives of the function f, or to find the integration of the function f over the domain AB. Okay, so in all these cases, since we do not know what is the function f explicitly, so what we are going to use? We are going to use the polynomial to evaluate the roots, to evaluate the derivatives, and to evaluate the integrals. Since we are using an approximate polynomial, what we are going to have? Approximating roots, approximating derivatives, and approximating integral values. At some points. Okay, remember that. Okay, so this is the major two uses with the approximating polynomials. Okay. Now let us look at some notations here. So f of x is the given function. F of x is the given function, and p of x is approximating polynomial so there is always a deviation is there. There is always a deviation is there. So the deviation of this is the exact and this is the approximate function. So the deviation is given by f of x minus p of x. F of x minus p of x for all the points of the domain. This is called the error of approximation. This is called the error of approximation. Okay. Now let us discuss how to construct this p of x. Means how to construct this approximating polynomial. Okay. So for this, we are assuming that. So we are going very initial stage. We are discussing the interpolation of the very initial stage. So we are considering very small nice properties of the function f. So that is, suppose assume that I'm assuming that let f of x be a continuous function on some closed and bounded interval a comma b. Okay, we do not know what is f of x explicitly. Okay, what is the expression for f of x? We do not know. But what we know in some particular problem, we know that the function is continuous. Okay, right. And what we know the values of f at some finite number of points. Say a is equal to x0, x1, x2, and so on, xn minus 1, and so on, and xn is equal to b. So that is, we know the values of the function at n plus 1 points only. Remember that. In this interval, how many points are there? Infinitely many points are there. But at every point, we do not know what is the value of the function f. But what we know only at some finite points and n plus 1 points. Particularly, we are assuming that we know the value of the function at the initial point a, and we also know the value of the function at the end point of the interval, that is b. So the initial point is represented with the x0, and then there are some intermediate points are there. So that is x1, x2, x3, and x4, and so on, xn minus 1 and xn. It is actually an increasing sequence. Increasing sequence. Okay. Now, these points are called nodal points. These points are called nodal points. Okay, nodal points means at the points at which we know the information, we know the values of the function f. Okay, right. Now we are interested here. One thing, two things can happen. One thing, the nodal points may be one thing, equispaced or non-equispaced. Equispaced or non-equispaced. Equispaced means what? Equispaced means the difference between the distance between the two consecutive nodal points is always same. That is, xi minus xi minus 1 is always equal to some constant h. The difference between the distance between the any two nodal points is always same, constant. So that is what we call the equispaced. Okay, or the discretization is uniform, or the uniform discretization of the interval a comma b. Non-equispaced means if it is not equispaced, we will call it as non-equispaced, which means there is a difference. The difference between the any two consecutive nodal points need not be same. Okay, right. Now, so we are interested in finding a polynomial, interpolation polynomial. So we are interested to find polynomial interpolation. Polynomial interpolation with the help of the values which we already know. With the help of values of f at nodal points. Okay, since we already know the data at some finite number of points, then while constructing the polynomial interpolation, why don't we use? If we use it, then we will get a better approximation, right? Okay, so the first thing is we are going to use the values of the functions f at the nodal points in constructing the interpolation polynomial. Okay. Now, what about if it is a polynomial, then what about the degree of the polynomial? If n plus 1 are points are given, then it is better to use the information at all the n plus 1 points. So basically, suppose let us see this one. This is A and this is B. As we said, A is nothing but x0 and x1, and B is nothing but xn, and before that xn minus 1. Right. So we know the value of this function at this point. We know the value of this function at this point, and this point, and this point we know. Okay. Now, I think it is clearly understood as the number of points, as the number of nodal points increased, the more we will get the better approximation, better interpolating polynomial. Why? Because we are utilizing the information from the information for the f at more nodal points. That is one thing. Now, suppose if only 2 points are there, then what is the polynomial that can cover these 2 points? that can cover these 2 points. There is a straight line. There is a straight line. Okay, straight line means degree of the polynomial is 1 here. So here number of points 2 and the degree of the polynomial yeah, that is what we call the linear polynomial. Okay, so the straight line basically. Then why you are using straight line only? Why can't we use some second order polynomials? Second order polynomials means, suppose, yes, why don't we consider a polynomial of this type? Think over it. Yeah, tell me, why don't we use what is called parabola kind of thing? This is also a polynomial, right? Parabola is also a polynomial, but it's a quadratic polynomial. Here the problem is, if you are using the quadratic polynomial only with the help of only with 2 values, see, look at this one, whether it is this polynomial or this one. Someone may come and someone may say, this is my approximating polynomial. So there is something called lack of uniqueness. Lack of uniqueness, right? Okay. So here, but in the straight line points, when we are having 2 points, there exists actually unique straight line. There exists actually unique straight line. So because of this uniqueness, when your 2 points are given, then it is better we go for the straight line rather than the quadratic more than the polynomial of degree more than 1. And the next, suppose if we know values of the function at 3 points, say these are the 3 points. Now, what about this one? What about this one? So here also you can have the uniqueness will come for the second order polynomial. Second order polynomial. That is nothing but second order polynomials are nothing but parabolas, right? Parabolas. Okay. Here not only that one, it is depends on the position of the points. We know the values of the function at 3 points. Say this one, and this one. Can we have a polynomial which passes through these 3 points? No. Only straight line we can have. Straight line we can have. So it depends on the position of the points also. But what we can say, if 3 points are there, we can use the approximating polynomial either a second order, that is quadratic, or linear. That is either using parabolas or using straight lines. We can use the approximation. Similarly, if we have 4 points, if we know the 4 points, then what we can use? We can use cubic polynomials, or sometimes we can use quadratic polynomials, or sometimes linear also. That depends on the position of the values. So in general, when we know the values of the function at n plus 1 points, what we can do, we can go for the polynomial degree maximum of less than or equal to n. So that is what here. Okay, finding an interpolation polynomial with the help of all the values at the nodal points. So the very first thing, the very first condition is what we can have. We can have the interpolation polynomial Pn of x should have the degree less than or equal to n, not more than that. Not more than that. Okay. Suppose if 2 points are there, we will go for the straight line linear approximation. If 3 points are there, we go for the quadratic approximation or the linear approximation. That depends on the position. Okay. And the next thing. Now we know the values of this function at this n points also. Why don't we use in constructing this polynomial? So we will use that. So what we know the values of the function at the nodal points. I actually runs from 0, 1, 2, and so on n. So n plus 1 nodal points are there. So at all these nodal points, I'll emphasize that the polynomial should coincide. The value of the polynomial should coincide with the value of the function f at the nodal points xi. Okay, for all I is equal to 0, 1, 2, 3, and so on n. Okay, such a polynomial is generally what we call the interpolating polynomial. Interpolating polynomial means a polynomial. Interpolating polynomial when we know the value of the function at n plus 1 points means first thing the polynomial should coincide with the function values at the nodal points, and the degree of the polynomial should not exceed n. Okay, the degree should be maximum of n, less than or equal to n. Okay. Now, what are the conditions? These two conditions are generally called the interpolating conditions. Interpolating conditions. So for the entire unit, we remember, okay, the conditions. Okay, that is fine. Now assume that we have calculated, we have determined Pn of x is determined. So Pn of x means okay, Pn of x means the interpolating polynomial of degree less than or equal to n. Okay, assume that we have evaluated what is Pn of x. Then for any y belongs to AB interval such that y is not equal to xi, what we can have, if you give any point of the domain, I can say the approximate value of the function f at the point y is the value of the polynomial at the point y. The value of the polynomial at the point y. Okay. It is approximately equal to. We are not saying that it is exactly equal to. Right? Okay. Now, this is the basic idea of constructing an interpolating polynomial. These 2 points we should consider throughout the process. Now, so let me start with some. There are different interpolation methods are there. So let me start with a very famous one. That is what we call the Lagrange interpolation. Lagrange interpolation. What is this Lagrange interpolation method says? The Lagrange interpolation method means, suppose assume that we have the point x where the nodal points are given as x0, x1, x2 and so on xn. And we know the value of the function, values of the function f at these nodal points. So I'm representing with f0, f1, f2 and so on fn. Here basically what is this fi? It basically means fi at xi. Okay, I is equal to 0, 1, 2 and so on n. So how many nodal points are there? N plus 1 nodal points are there. N plus 1 nodal points are there. Okay, right. Oh, okay. F0 means, yeah, F0 means, sorry, it is not Fi at xi, it is F at xi. It is F at xi. Okay, right. Now, since n plus 1 points are there, what could be, what is the degree of the polynomial? Degree of the polynomial should not exceed n. So that is less than or equal to data because of the because of the given data. And not only that, the interpolating polynomial Pn of x must satisfy the function values for all x is equal to x at all the nodal points. At all the nodal points, function value and the polynomial value should be same. Okay. So the Lagrange method, the Lagrange interpolation method considers the interpolating polynomial will be of the form here. The interpolating polynomial will be of the form here. F0, capital F0 times x plus capital F1 of x times F2. What is F0? F0, sorry, it is not F2, it is F1. What is F0, F1, F2, and so on F1? They are scalars, they are values, right? And plus capital F2 of x times small f2 plus and so on plus capital Fn of x times Fn. So what is the basically, this is the interpolating conditions, and the degree of Pn of x has to be less than or equal to n. So we are assuming that Pn of x is of the form in this format where the capital Fi of x are nothing but each one is a polynomial. Each one is a polynomial of degree less than or equal to n. Sorry, not less than or equal to n. Equal to n. Okay, so look at this one. So this is a polynomial of degree less equal to n. This is also a polynomial of degree equal to n. This is also a polynomial of degree equal to n. And similarly, Fn of x is also polynomial of degree equal to n. Okay. Now, what about the linear combination? What is this one? This is the linear combination of polynomials of degree equal to n. So because of this reason implies this basically gives us this condition is satisfied. Implies this condition will be satisfied. So this condition is considered already. The linear, this one is a polynomial of degree n. This is polynomial of degree n, polynomial of degree n, polynomial of degree n. So this entire thing is a linear combination of polynomials of degree equal to n, and hence the degree of the polynomial is cannot exceed n. It will be less than or equal to n. Sometimes it is not necessarily equal to n. Okay. For example, x square plus 1 is one polynomial of degree 2 plus minus x square plus x plus 1. This is also a polynomial of degree 2. But what is the sum? What is the linear combination? Linear combination is x plus 2. So that is a polynomial of degree 1 only, not 2. Okay. Sometimes while adding, the degree may reduce, but definitely it will not increase. Right? Yeah. So here the degree of the polynomial Pn of x is less than or equal to n. So this condition is satisfied. Right. Now, what about the one more condition is there, right? What about the one more condition? What is the other condition? This is Pn at xi should be equal to f at xi. Okay, let us evaluate what is, if this is the polynomial we are talking about, then let us evaluate what is Pn at xi is equal to, basically this is equal to what? According to the assumption, it is equal to capital F0 at xi times F0 plus capital F1 at xi times F1 plus capital F2 of xi times F2 plus and so on plus capital Fn of xi at Fn, which is equal to, further equal to, since xi is a nodal point, so value of the polynomial at this nodal point must be equal to the value of the function at that point. Value of the function at that point. Okay, this should be true for all I is equal to 0, 1, 2 and so on n. 0, 1, 2 and so on n. Okay, if you look at for the arbitrary I, then we may not understand clearly. So for I is equal to 0, let us see what is happening. So that is Pn of x0 is equal to f0 x0 times f0 plus f1 x0 times f1 plus and so on plus fn x0 times fn is equal to value of the function f at x0. Now you tell me what are the possibilities now for this function, for these things. What are the possibilities? What are the possibilities? What are the possibilities? What are the possibilities? Here, what is here? F at x0, f at x0 is nothing but f0. Now you compare on both the sides, left hand side and the right hand side. Left hand side and the right hand side. So if we assume that f0 at x0 is equal to 1 and f1 at x0 is equal to 0, f2 at x0 is equal to 0 and so on, fn at x0 is equal to 0. This is a polynomial. Polynomial at x0, I am assuming it should be 0, and this is a polynomial at x0. This is also it is also 0, and similarly the polynomial fn at x0 is 0. But the polynomial f0 at x0 should be equal to 1. So the polynomial f0. Okay, now let us evaluate I is equal to 1 case also. Then we will conclude. If I is equal to 1, Pn at x1 is equal to f0 x1 times f0 plus f1 x1 times f1 plus f2 x2 times small f2 plus and so on plus fn x1, sorry, this is 1, times fn is equal to f at x1, because the polynomial value and the functional value should be same at the nodal points, but that is nothing but f1. Now you look at here. Now you look at here. So this one we are assuming that f1 x1 is equal to 1 and f0 x1 is equal to 0, f2 x1 is equal to 0 and so on, fn at x1 is equal to 0. Right? So if we construct the functions, see here, the basic idea is to find out what is Pn of x. Basic idea is to find out what is Pn of x. Right? So to find what is Pn of x, what we should know, according to the assumption, what we should know? We should know what is f0 of x. We should know what is f1 of x. We should know what is f2 of x. We should know what is fn of x. So this is how the Lagrange method, the Lagrange interpolation method goes. Okay. So what about the conditions on fi? So the conditions on fi is basically the coefficient polynomials. So that is fi at xi, xj is assumed to be either 1 or 0. The polynomial fi is a polynomial at some nodal point xj is equal to 1 when I is equal to j. When I is not equal to j, we are assuming that the polynomial fi vanishes at xj. Remember here, recall each, this should be true for I is equal to 0, 1, 2, and so on, all the coefficient polynomials. Recall that each fi of x is a polynomial of degree equal to n, and not only that one, fi at x naught is equal to 0, comma, fi at x1 is equal to 0, comma, fi minus 1 at xi is equal to 0, comma, fi plus 1 at xi is equal to 0, comma, and so on, fn at xi is equal to 0. So the value of the function fi vanishes at all the other nodal points, and not only that one, the value of the polynomial fi at xi is equal to 1. That is how we are constructing the functions. This is the construction process. Remember that. Okay. Okay. Now, how many are there here? 1, 2 root, second root, I minus 1 root, I plus 1 root, and some nth root. What is fi? Fi is a polynomial of degree n. Okay. But what are these? X0, x1, xi minus. So yeah. Yes, right. No, here I have done something mistake here. It is not. Yeah. fi at xi minus 1 and fy at xi plus 1. This is fi at xn. Okay. So when we have some n plus 1 points, x0 to xn with x1, x2, and xi minus 1, xi plus 1, and so on. If you take any coefficient polynomial that is not vanishing at this point, but at this point vanishing, at this point, at this point, at this point, at this point, at all other points. So out of n plus 1 points, at one point it is taking value 1, and at remaining all other points it is taking 0, which means how many roots are there? It is a polynomial of n, right? Polynomial of degree exactly equal to n. So what are the maximum roots possible for the polynomial? Obviously n. And what are the roots? The roots for fi is nothing but x0, x1, x2, xi minus 1, and except xi, remaining all other points are the roots. So if this is the case, then fi of x is nothing but okay. Suppose now you see here x is equal to a and x is equal to b. Give me a quadratic polynomial, means polynomial of order 2 with the roots a and b. Can you give me that? Can you give me a polynomial, a second order polynomial, second degree polynomial, okay, with the roots a and b? What is that one? Simply x minus a times x minus b. Okay, not only that one, there should be some constant alpha I. Constant times a polynomial will not change the degree, right? So we should have some constant also should be there here, x minus 1, x minus b. Suppose if it is asked, give me a polynomial of order 3 with 3 roots A, B, C, then what is that one? It will be some constant times x minus A times x minus B times x minus C. So now here, that is what you should understand. That is what you should understand. Fi of x, each coefficient polynomial is a polynomial of degree n, and we know what are the roots also. That is how the construction is happening. So it is simply alpha I times, that is a constant times x minus x naught, x minus x1, x minus x2, and so on, x minus xi minus 1, x minus xi plus 1, and so on, x minus xn. Okay. So for the simplicity, let me write at least two polynomials, alpha f naught of x, that is alpha naught times at x naught, f naught x naught is non-zero number. So x naught is not the root for f naught. So it will start from x minus x1, x minus x2, and so on, x minus xn. Now what is f1 of x? Alpha 1 constant times x minus x naught. X naught is a root. X minus x2, x minus x1 is missing. Why? Because at x1, f1 x1 value is 1. So that is non-zero number. So that is x1 is not a root. And so on, x minus xn. So similarly, all other things also there. So in evaluate, okay. So this is where I will stop the section. It is already 12:22. So tomorrow, what we will do? Tomorrow, the construction process will continue tomorrow also, and we will do some exercises also tomorrow on the Lagrange interpolation method. So far, do you have any doubts? If you have any doubts, you are most welcome to ask. Thank you all.